In this video, we're going to talk about another way to approximate function values, and that's using differentials. You may have seen something like this in your first calculus course. So we're going to start by reviewing the situation for differentials with a function y is equal to f of x. The differential dy is defined as f prime of x dx and is approximately equal to delta y. We're going to take a look graphically at what these things represent. So if we have the graph of a function f of x, and we have the tangent line to that function at some point where x is equal to a, if we move over a short distance, so if we move over a short distance dx, so that we're looking at a point a plus dx, we can evaluate that point in the tangent line and in the function. The differential dy is that distance there. And the differential dx, we've already got that on the bottom here. And delta y is the difference between the function value at a and the function value at a plus delta x. So the idea here is that these two values, dy and delta y, they are very close. And so if I want to approximate the function value, this value here, f of a plus delta x, I can take this value here. And this value here is, well, it's the function value f of a plus the vertical distance dy. So this f of a plus dy. And that's the approximation, that f of a plus dx, well, f of a plus dx is equal to f of a plus delta y, and it's approximately equal to f of a plus dy. And since dy is defined as f prime of x times dx, and we're at a point where x equals a, this is f of a plus f prime of a times dx. And that is a differential approximation for a function of one variable. Now we're going to go and look at multivariable functions and define analogous differentials and analogous approximations using them. So if we have z as a function of f of xy, if it's a differentiable function, then the total differential of z is defined as dz is f sub x of xy times dx plus f sub y of xy times dy. And if we have a function of n variables, if w is equal to f of x1 through xn, then the total differential of w is dw is f sub x1 of x1 through xn times dx1 summed up. Total differential all the way to f sub xn of x1 up to xn times d of xn. Approximating differentials, we're going to use exactly this same idea that we did for a function of a single variable for two variables. So f of a plus delta x and b plus delta y, that means some distance away from the point AB, is f of ab plus dz. That's the analogous statement to here. And if we replace the dz by the definition of the total differential, we get this approximation. And we can do the exact same thing for a function of n variables, where the function at a plus a1 plus d of x1, etc., up to an plus d of xn is the function value approximately plus dw. Replacing dw by the total differential, we get this approximation for a function of n variables. In the next video, we will do a differential approximation for our function here, z is equal to f of xy. So we'll be using the differential approximation for a function of two variables.